Hello, this is Ian Harper welcoming you to Business of Weather podcast, produced in association with Asia Climate Forum, Asia's largest event dedicated to extreme weather and climate change, flooding and poor air quality. In each episode, we'll investigate the increasing impact of extreme weather and climate change on business and society, and look at how weather technology and climate information services can help address the growing challenges. We'll also spotlight the new opportunities for entrepreneurs and business startups seeking to develop the business potential of technology innovations to help those affected by extreme weather. Each year, tornadoes can kill or injure hundreds or even thousands of people and cause billions of dollars worth of economic damage. As with other extreme weather events, they also tend to have a greater impact on less well-off areas of the world. While tornadoes are a global phenomenon, most occur in the United States, where in an average year they kill about 70 people and cause some $500 million of economic damage. While the US has recently experienced one of its worst tornado outbreaks of the past decade, there is no clear evidence that the number and intensity of tornadoes is related to climate change. Tornadoes form when warm, humid air collides with cold, dry air. The warm air rises through the colder air, creating an updraft, and this will rotate rapidly if winds vary sharply in speed or direction. The average tornado is about 200 meters wide, moves at about 40 kilometers an hour, and travels about 8 kilometers before dying out. However, massive tornadoes, the ones capable of widespread destruction and many deaths, can roar along at up to 400 kilometers an hour. Such giants can be over a kilometer tall. They can tear homes and businesses apart, destroy bridges, flip trains, and send cars and trucks flying. They can uproot trees, suck water from a riverbed, and destroy communications and power infrastructure. The precise prediction and tracking of tornadoes is not yet a reality. Meteorologists can issue warnings when atmospheric conditions are right for their development. They can use radar to track the path of thunderstorms that might produce tornadoes. But while modern Doppler radars are making it possible to more accurately detect tornadoes, much remains to be done. However, recent research involving sound could, in conjunction with modern radar tools, significantly increase the accuracy of tornado forecasting. The research carried out by engineer Brian Elbing of Oklahoma State University shows that tornadoes emit low-frequency sounds which can be picked up by microphones and help accurately pinpoint the size and location of an impending twister and so better warn communities. Business of Weather spoke to Brian Elbing to learn more about this exciting development. Welcome, Brian.
Hello.
Right, let's start at the beginning. What exactly is a tornado? And how destructive can they be?
A tornado it's a rapidly rotating column of air, and depending on the size of it, it can be very destructive. It can destroy large buildings quite easily.
Right, now, without getting too technical, please tell me about your research into detecting tornadoes before they actually form by listening out for the sound they produce.
Yeah, we've observed that tornadoes emit infrasound while they're forming as well as when they're on the ground. And what we're doing is we're trying to take those observations and answer questions about what is making the sound inside the tornado so that we can use it to improve tornado warnings.
What exactly is infrasound and what led you to look at it in the first place?
Infrasounds is simply sound that's at frequencies below human hearing. And there's been past researchers that have observed this, that there seems to be a relationship between when tornadoes would form and infrasound would occur.
What sort of frequency are we talking about? 1 hertz, 2 hertz?
It falls generally between 1 and 10 hertz, and humans can hear down to 20 hertz, so it's just below human hearing.
Okay, so tell me, how does the system you devised work in practice? And how much early warning of a tornado could it actually provide?
Well, what we're doing right now is we currently have 3 microphones that are out recording the atmosphere at all times. We use the slight difference between each microphone, what it hears, to determine the direction that the sound's coming from. This is just like how you use your 2 ears and your brain processes the difference between the two to figure out which direction somebody is located when they're speaking to you. So we're doing the same thing to get the direction of the sound. Next tornado season, we plan on deploying a second array of these microphones. And so if we have the direction from 2 different locations, you can start to identify the exact location where the sound's being made. As for how early you can detect it, that's still an open question, but there seems to be a correlation between the larger the tornado, the earlier the signal is picked up. We recorded one in May of 2017. It was a very small tornado that had no warning issued on it, but we had picked up the signal associated with the tornado 4 minutes before it touched ground.
Right. You mentioned 3 microphones and an array of microphones. Where exactly are they, and are they portable?
They're right now located near our campus. We have them on the ground, and the current setup is not portable, but we are developing a couple mobile units that we can deploy rapidly to get in better position during a storm.
Right. I mean, are you close to actually having a system which is operational?
Well, I think so. We have the measurements aren't necessarily the issue. There's a few things that need to be improved, particularly getting wind noise down. But the bigger thing that's holding it back is answering the fundamental question about what's making the sound. So you can imagine, when you're an infant and you first hear something, you can figure out that there's something behind you with practice by hearing that difference, turning around, seeing what it is. You learn that. We need to do the learning side. We're picking up the signals. Now we need to know what that is. And then once we know that, we can just listen and know what's going on around us, just like we do when we're in a noisy room listening to somebody.
Have you any thoughts on what might be producing that sound?
Yeah, we have kind of 3 working hypotheses about what's producing the sound. One of them is the idea of if you picture the tornado as like a cylinder, that the diameter is expanding and contracting, that could be making the sound. And there's some consistencies in what we've observed with what that would predict. There's also one that's a little more complicated, and it's how it gets formulated. But the interesting part is that this different formulation of the governing equations points to the ability to emit sound, and it also is the only formulation that's accurately predicted the pressure inside of a tornado. No other theory we have has ever predicted the few measurements that we have. And then the third one is that it could be a heat effect. So you can picture if I heat up air and then I cool it down, that's expanding and contracting the air, which is what sound is.
Right. Do you think your system, based on detecting infrasound signals, is likely to be more reliable than existing tornado early warning systems?
We don't expect this to replace radar and what's currently in place. But what I don't think people understand is that with tornado warnings, right now 70 to 80% of them are false. So you get false alarms most of the time. And in a place like Oklahoma, where tornadoes are very frequent, people just ignore them. And so the hope here is that this is more information that's completely independent of anything we're currently using. And so general rule of thumb is the more independent information you have that's reliable, the better chance you have of getting the correct answer. And so we really view this more as getting the false alarm rate down with a new source of information.
How important is data or information to the functioning of your system, and where do you get the data from?
Yeah, it's quite critical at this point, because if you think about what I was just saying, that we need to answer fundamental questions. What we truly need right now is reliable measurements of the acoustics, as well as the flow structure of the tornado. And that's really only possible if it occurs really close to a radar site, and at that same time we also have microphones close to that same location. Radar only can see line of sight, and so the curvature of the earth heavily limits how far they can actually see the actual tornado. Infrasound, this is one of the benefits of infrasound is not line of sight. It depending on the frequency, it can travel all the way around the earth, actually.
Like whale noises.
Yeah, really long distances. There's a lot of evidence that the animal kingdom uses infrasound to find water, to avoid storm systems. So there's a lot from nature that indicates that this is what they use.
Oh, interesting. Now then, what are the potential business opportunities opened up by your research? Do you have any plans yourself to commercialize it, for example, by developing a tornado early warning system?
I don't have plans to commercialize it, as my primary focus is answering the fundamental questions. But I have been working actually with a small startup company that they've been looking at developing this for both tornado warnings as well as clear air turbulence. And so I've been willing to test some of their microphones against some established ones and share information with them to help them commercialize it.
Right. Now, do you think there could be any other instances where low-frequency sound or infrasound can help warn of other types of dangerous or extreme weather events?
Yeah, I mean, infrasound actually has several applications already in use besides the clear air turbulence possibility that I just mentioned, which you can imagine that'd be great if pilots could avoid those turbulent situations when they're flying. The other applications for weather or natural sources would be they're used right now for studying earthquakes. There's a lot of coupling between the waves that transmit through the ground and in the air. It's also heavily used for studying volcano eruptions and quantifying how much ash is being emitted during an eruption. And then also there's some evidence right now that it might be used to detect heart disease in people. And historically, how it's been used is to monitor for any above-ground nuclear bomb testing.
Right. Okay, then, now, just to conclude, how can listeners follow up on your work?
The best way is at my website, flowphysicslab.org, or you can follow me on Instagram at flowphysicslab or Twitter at elbingprof.
Excellent. Well, Brian Elbing, thank you very much.
Thank you.
You're listening to Business of Weather, produced in association with Asia Climate Forum, Asia's largest event dedicated to addressing extreme weather and climate change, flooding, and poor air quality.